Hello and welcome back to my YouTube channel. My name is Professor Gavala, and today I'm going to be talking to you about the high frequency small signal analysis of a common source amplifier, where the small signal model is right here located to the right. And before we dive into where the small signal model is located here to the right, and we're tasked with finding this AV gain, or the V out over V in of this small signal model. Before we dive in, I will encourage the viewers to check out two videos. Both of them are posted in the description below, and I will tag both videos in the top right hand corner of this video, where the first video is the common source amplifier, where I go into depth of analyzing this circuit without these capacitors connected. And the second video is called Miller's Effect Examples, High Frequency Model of a MOSFET, where I introduce why these parasitic capacitances are attached to this MOSFET. Okay, now before we go in, we want to notice that this CSB is not located in this small signal model. And again, the reason is because on both ends of CSB, we are connected to ground, so we can ignore it. Now, going on to the high frequency analysis of this common source amplifier, the first thing I'm going to do is note that I have a node here, and I'm going to call this V1. And I have another node here I'm going to call Vout. And essentially what I'm going to do is I'm going to use KCL at both of these nodes, where KCL is the fundamental to nodal analysis. So you can either use nodal analysis or KCL. And I'm going to say that at Vout, I have currents leaving the node. Call this I1, call this I2, call this I3, and call this I4. And as well as at V1, I have currents leaving this node as well. Call this I5, call this I6, and call this I7. Now, the goal here is to write some KCL equations at V1 and at Vout, and then manipulate these equations to get an AV gain of Vout over Vin. So the first thing I'm going to write is the KCL at Vout. And again, this is essentially nodal analysis, which says then that I1 plus I2 plus I3 plus I4 must equate to 0, or that all my currents leaving the node have to equate to 0. And I1 is essentially Vout minus V1 times CGDS, which is in the frequency domain, plus I2, which is GM-V1, plus I3, which is Vout CDBS, plus I4, which is Vout over RD, have to equate to 0. And let me call this equation number 1. Okay, so then the next thing I'm going to do is I'm going to write a KCL at V1. And again, this says then that I5 plus I6 plus I7 have to equate to 0. And essentially, I5 is V1 minus Vn over Rg plus V1 times CGS times S, plus an I7 is V1 minus Vout times CGDS, have to equate to 0. And this is my equation number 2. Okay, so given these two equations, the goal here, I'm going to start this, is essentially to eliminate V1 and find Vout in terms of Vn. So this is the ultimate goal, and we will start to analyze that now. Okay, so what I've done here is I've written both my equations on a new page. And the idea here is to use equation 2 to solve for V1. And then once I solve for V1, I'm going to plug V1 into equation 1 and then solve for V out in terms of Vn. All right, so let's go ahead and take equation 2. And then I can say then that V1 times 1 over Rg plus CGS times S plus CGDS has to equate to Vn 1 over Rg plus Vout CGDS. So then I can go ahead and say then that V1 1 plus Rg CGS times S plus Rg CGD times S. And this is again to get a common denominator of Rg across all terms. Has to equate to, again, this Vn times 1 over Rg plus Vout times CGD times S. So then I get V1 is equals to Vn. In my numerator, I just get 1 simply because this Rg cancels out with this one here. And in my denominator, I get 1 plus Rg CGS times S plus Rg CGD times S plus Vout. My numerator, my Vout is going to be Rg CGD times S over 1 plus Rg CGS times S plus Rg CGD times S. Okay, again, pause the video to make sure you're following along. If you have any questions, please leave them down in the comment section below, and I'll be sure to get back to you. So what I'm going to do here is I'm going to say then that this term here, I'm going to call A, and this term here, I'm going to call B. So then I'm going to say that V1 is equals to this Vn times A plus Vout times B. And I'm going to say that this is what I call my equation number 3. Okay, so the idea now is to take equation number 3 and plug it into V1 of equation number 1. But first, I'm going to simplify equation 1 by taking out a Vout and multiplying it by CGDS plus CDBS plus 1 over Rd plus V1 GM minus CGDS is equated to 0. So let me go ahead and plug in V1 and find a common denominator for this term. And I can say then that Vout, this becomes RDCGDS plus RDCDBS plus 1 all over RD. Plug in V1, I get Vn times A plus Vout times B times GM minus CGDS has to equate to 0. So then what I can do here is I can name another variable. I can call this C. And so what happens now? So then Vout times C plus Vn times A times GM minus CGDS plus Vout times B times GM minus CGDS has to equate to 0. I can pull out a Vout, and I'm left with C plus B times GM minus CGDS, and that is equated to Vn times A, and I'm going to switch these two terms because it's going to be a minus. I hope that makes sense. So this is C GDS minus GM is equated to 0. So then essentially now what I get is that V out over V in, as you can see, will be A times C GDS minus GM over C plus B times GM minus CGDS. And this here can technically be your answer because A, B, and C and all the other components are given parameters like your transconductance, your capacitors, and your resistors, right? But let's go ahead and dive in to substituting A, B, and C into the equation and simplifying it into a nice form. So given this equation, I can go ahead and equate this to my numerator will be C GDS minus GM, and my denominator will just be the denominator from A, which is 1 plus RG CGSS plus RG CGDS. And then in my denominator, I get this long equation, which is going to be C, which is RDCGDS plus RDCDB S plus 1 over RD plus RGCGDS times GM minus CGDS over 1 plus RGCGSS plus RGCGDS. So I hope that makes sense. Essentially, these terms are coming from A, C, and B. Okay, so if we keep on going, what I'm going to do is I'm going to copy this and I'm going to paste it. And what I'll do is I'll erase this denominator. And what I'll do is I'll rewrite the denominator. And it's going to look something like this. RDCGDS plus RDCDBS plus 1 times 1 plus RGCGSS plus RGCGDS plus RD times RGCGDS times GM minus CGDS. And then my common denominator for all of this will be RD times 1 plus RGCGSS plus RGCGDS. And as you can see, the reason for doing that is because now this denominator cancels out with this denominator. And this RD then appears on the numerator up here. So then if we go ahead and clean that up, what do we get? We get that V out over V in is equated to this RD CGDS minus GM over RDCGDS plus RDCDBS plus 1 times RGCGDS plus RGCGSS plus 1 plus RD times RGCGDS times GM minus CGDS. All right, so I hope this makes sense so far. And the last thing we need to do is we need to distribute this term in here and this terms into here and see if we can eliminate some common terms and then finalize our denominator and our final equation. So what does that look like? So what I'm going to do here is I'm going to just take the denominator and I'm going to write some terms. So I'm going to write out RG, RD, CGD squared S squared plus RG, CGS, RD times CGD S squared plus RD times CGD. This is this term multiplied by all three of these terms. And then I get plus RD times CDBS squared RG CGD plus RD times CDBS squared RG times CGS plus RD times CDBS, and that is this term times all three of these terms. And then I get a plus RG times CGDS plus RG times CGSS plus 1. And again, that's just this 1 times all three of these terms. So then the last thing that I get is plus RD, RG, CGDS times GM, which is essentially all these terms times GM. And then minus RD, RG, CGDS squared times CGD. And that is all three of these terms times this last term here. And what we notice is that this term cancels out with this first term here. So now what I can do is I can write my final equation, and I can say final equation. And I can say then that V out over Vn is equated to this RD times CGDS minus GM. And then the denominator, we have this CGS, CGD plus CDB, CGD plus CDB, CGS times RG, RDS squared. Again, that's coming from all my S terms. So this term here, and this term here. And then the next term, which is the S terms, is going to be this RD times CGD plus CDB plus RG times CGS plus CGD times 1 GM RD, closes, S plus 1. And again, the S terms are going to be this term, this term, this term, and this term. And obviously the one term is just simply here. All right, so this here is your final equation, and basically answering in full form the question that was asked at the beginning of the video. So now a key note, which I've talked about in the common source amplifier video posted in the description below. If we consider that V out over Vn for S is equals to J omega, and omega is equals to 0, we're going to notice that this term goes away, it goes to 0, and this term goes away, it goes to 0, and this term here goes away, it goes to 0. So then this is going to be basically close to minus GM RD, which was the answer to the common source amplifier circuit that we solved. All right, in the next video, I'll be doing the same example, but considering what's called Miller's effect. And additionally, I'll be explaining what the frequency response should look like in the next video after that. If you like the video, please give it a thumbs up and please share the video. If you like what the YouTube channel is providing, please consider subscribing. It really helps the algorithm. Thank you.